Now we're going to consider a mass m at distance capital R from an axis of rotation, and a force perpendicular. Okay, that mass m is going to be connected to the axis of rotation by a strong rod. We're now going to consider a mass m supported by a strong rod, but a strong rod of negligible mass that's constrained to rotate about a point. So this whole mass and rod system is constrained to rotate about this point. And a force, F, perpendicular to the rod at distance r from the axis. Now we're going to keep that force perpendicular to the axis as the rod rotates. So if this system has angular velocity omega, its kinetic energy is what? It's 1/2 mv squared, where m is the mass and v is how fast it's moving. But v, how fast it's moving, is the product of its angular velocity and how far it is from the axis of rotation. And we want this expression in terms of m, big R, and omega. So there's our expression for kinetic energy. Now what's the work done by the force F when rotating through angle delta theta? Now let's back up a second and specify that this will be the net force acting on this system. So I'm going to write a net there under my F's. So now if this system rotates through an angle delta theta, the work done by the net force is the work done by the net force, okay? And the net force is going to move through some angle. So the work done by the net force is the perpendicular component of the net force times the displacement. But for any short time interval, any time increment, the force is perpendicular to the displacement, as we can see by the fact that this point is going to describe a circle, and this net force is always going to be tangent to the circle, being perpendicular to this rod. So the work done by the net force is then just F net times the distance around that circle. All the distance you go around the circle when the angular position changes by delta theta is just r delta theta, the number of radians multiplied by the radius, so that the force is acting through this distance. And that's of course then equal to r times F net delta theta, and that's very much analogous to F net delta S, where F net is the RF net, and F net is replaced by RF net when delta S is replaced by delta theta. More about that soon. Okay, so the work done by the net force can be expressed this way, as RF net times delta theta. Now this RF net is going to have a name in a minute, but we'll just say for now that we have this expression. So change in kinetic energy then is what? It's RF net times delta theta, the work done by the net force. If the initial velocity is 0, then the final velocity is r times F net delta theta. Okay, now this quantity RF perpendicular, okay, well, let's think about this a minute. If I applied the same force out a little further, first of all, intuitively, we might well understand that that's going to give us more leverage, more torque. More leverage, the force is going to have more leverage, it's going to have more effect. The way we're going to connect that here is simply that if the force is further out, then through given delta theta, that force is going to act over a longer arc and do more work, which will increase the kinetic energy more, which will give us a greater velocity. So the further out this same force applies, the greater the distance through which it will act as position changes by angular position changes by delta theta. Therefore, the greater the kinetic energy and the greater the final velocity. Okay, well, that means that in order to change the angular velocity of the system, both the magnitude of the force F net and the magnitude, at least a component of that force, perpendicular to the system, perpendicular to the axis, to the rod in this case, is going to have its effect. That force is going to have its effect. I lost the train of my sentence, but that force is going to have its effect, as is the distance from the axis. Okay? And the kinetic energy gained is going to be a function of the product of that distance from the axis and the net force. So this R times F perpendicular, now I say F perpendicular because if the force was acting out in this direction, then the component of the force here would have no effect on the system, no accelerating effect on the system, only the component perpendicular to the what we're going to call the moment arm, a vector from here to here, but we'll talk about that later. Okay, well, only the component perpendicular to this rod is going to have an effect in accelerating the system. For that reason, it's just the RF perpendicular. That's what we call the torque exerted by the force F at position R relative to the axis. Now, this becomes a vector definition. We'll make it more formally shortly, but this leads us to the definition of torque, which is a Greek tau, and it's a vector, and it's going to be R cross F, an R vector cross an F vector. Now, the R vector and the F vector in this case, well, I'm going to write those in. The R vector extends from the axis of rotation to the point at which the force is applied, and we can kind of extend that to the point where the line of the force intersects the R vector, but we'll look at that a little bit later on. Okay, so there's the R vector, and here is a general force vector. The perpendicular component of this force vector is equal to the F net that we talked about before. So it would be the perpendicular component of this F vector and the R vector that would determine how much velocity is attained as we rotate through a given angle. Okay? And we express that as tau equals the R vector cross the F vector. Now we'll talk more about what that means, but that's our definition of torque. And I'll comment that in this case, the R vector is in this direction, the F vector is in this direction, so R cross F is going to be in this direction. We'll discuss in more length why it's appropriate to have the R vector out of the plane. There is no vector in the plane that could describe, there's no single vector in the plane that could describe that rotation. Okay, so from this example, we see how the kinetic energy changes due to a force at a position, and we see that if we define torque as R cross F, then the final kinetic energy is going to be torque times delta theta. So I can also write don't have a good place. That the change in kinetic energy is tau delta theta. I should have said that the work done is tau delta theta. And if you have, if F is the net force, then the change in kinetic energy will be tau delta theta. So let me modify that. Okay. Because R cross F equals just R times F, if R and F are perpendicular, then in this case at least, the work done is the torque times delta theta. Now delta theta should be a vector, as should tau, and it's really tau dot delta theta. The work is that. Now we'll come back to that. Just a brief introduction to this idea in terms of this situation. one more final statement to summarize. The work done is equal to your torque multiplied by delta theta. Well, the dot product of your torque with your delta theta, where your torque is defined like this. The definition motivated by our analysis of this original situation, but applying to a situation where the force can be in any direction. The cross product takes care of that and gives us considers only the perpendicular component of the force. And then if we use tau net dot delta theta, that's the work done by the net force, which is therefore equal to the change in kinetic energy by the work kinetic energy theorem.